Okay. Now, in case you are thinking, and so I will remind you once again, I know you know this already, but it doesn't hurt to sort of remember what these objects mean. So, what exactly is mu hat? This is
Malabika,
the
sorry.
food. Yeah,
Hi. Sorry to interrupt. So
no
I have
problem.
not introduced the notion of Fourier dimension. I have
Yes,
only shown them that the energy integral can be written, using it can be reformulated using the frequency variables. So
yes.
yes, I've just
Yeah,
mentioned that.
no
Yeah,
problem. So, I'm
yeah,
not going to assume that they know anything about Fourier dimension. I'm going to sort of build it up and then go ahead with it.
great. Yeah, sure.
Okay, thank you, Ashwin. It's good to know. So, what exactly is mu hat? Mu hat is the Fourier transform of mu. So, and how is it defined? It's mu hat of xi is the integral of e to the power minus 2 pi I xi d mu x. Okay. So, all right. So, I want to sort of place this new concept in context. Um, what exactly does the Fourier transform do, and why is such an object even a measure of size? So, perhaps a good way to sort of build intuition for this is to look at some examples. One is, let's start with, let's say, the set E, which is a singleton. And you can extend this to finite points, let's say. So the only measure supported on E, so only probability measure on E is the Dirac delta. Okay. So that means, and its Fourier transform is identically 1, no decay, and the Fourier dimension of this E is 0. Okay. And this sort of agrees with our notion that singletons or finite point sets should have 0 dimension. Similarly, let's test out another intuitively clear um, example. Let's say we choose E to be the full interval 0 to 1. And then, as you can see that, let's say the probability measure mu of x on E is the indicator function of 0, 1. And if you calculate mu hat of psi, this one actually we can do by hand. Okay. And if you take the absolute value of this decays like a constant over absolute value of psi. So that means that beta, the largest possible beta, is 1. So the Fourier dimension of 0, 1 is 1. Okay. And I just want to give one more examples, and then I will stop for your questions. Um, something that is not very clear, at least of the just from the definition, is the relation between Hausdorff dimension and Fourier dimension and Minkowski dimension. So there is an important result in geometric measure theory which tells you what the relation is. It sometimes goes by the name of Frossman's lemma. Sometimes Frossman's lemma means something else, but it's a consequence of that lemma. So in any case, I'm just going to call it Frossman's lemma. And it shows that the Fourier dimension for any set, any Borel set, is always dominated by the Hausdorff dimension. And the Hausdorff dimension in turn is dominated by Minkowski. That's well known, but that's not Frossman. Okay, so this one, I will just put it on the side. This one is bounded above by Minkowski. Okay. And in fact, whoops, where did I go? Okay. So in fact, and this inequality can be strict. So this inequality here okay. For example, the important example is the Cantor middle third set. So E is its Hausdorff dimension, as we were talking about yesterday, is log 2 over log 3, but its Fourier dimension is 0. Okay, so it gives rise, this kind of an inequality gives rise to the intuition that sets with large Fourier dimension are somehow richer in structure than sets of large Hausdorff dimension. So sets of large Fourier dimension are richer. And I'll put this in quotes because how you uh, determine rich is sort of in the eye of the beholder um, in certain properties than sets of similar Hausdorff dimension. Okay, so let me pause for a moment and see if there are any questions. I'm sure there will be, but let me ask. Any questions so far?
Yeah. Could you show the definition of the Fourier dimension again?
Sure, yes, of course. Let's see here.
So we don't talk about Fourier dimensions, at least for now, of sets in R2 or R3.
R2, yeah, one can do it in any dimension. So let me just put it here just for reference. Today I was not going to talk about this, but let's see. So you could say that instead of this, one could take any set in RD, D greater than or equal to 1, in which case, instead of 0 to 1, this would be replaced by 0 to D, and everything else remains unchanged. But for today, we were just going to deal with D equals 1.
Right. Okay. Thank you.
Okay. Any other questions? Okay. If not, so let's continue then. What we are going to do next is to try to unravel what it means for what does this word richer mean? Richer in what sense? So this is open to many interpretation, but today's goal is we are going to show that sets of large Hausdorff dimension is richer in capturing patterns. So let me state the result, and then we are going to sort of do the comparison afterwards. Okay, so the main result for today is the following. Suppose, so consider the class of functions f sub a, b, c, where a, b, c are positive integers with the property, as I told you earlier today, a plus b has to be equal to c, and f(a)(b)(c) is a linear function it's the function ax plus by minus cz. Okay, so this is the class of translation invariant linear equations or linear functions in 3 variables with integer coefficients. Okay, the main result to be contrasted with earlier ones is the following. If the Fourier dimension of a set E is larger than 2/3 and E is a subset of R, and then it must contain a non-trivial solution to some a non-trivial solution of some equation of the form f abc xyz equal to 0. And what does that actually mean? It means, i.e., there exist distinct xyz in E such that ax plus by equal to cz for some a, b, and c. And the reason I wanted you to, I want to sort of remind you of what the counterpoint result looks like. So I want you to compare this condition here. Okay. So let's compare this with the following result. It's by many people, but perhaps the strongest one to date is due to Mattei. Um, there exists a set. There exists a set E subset of 0, 1 of full Hausdorff dimension that contains no non-trivial solution for any f ABC equal to 0, um, f in script f. So these are rather almost contradictory looking statements. The distinction is, of course, in the notion of size that we use to quantify these sets. What it says is that if for Hausdorff dimension, it is possible to avoid all kinds of linear patterns and still retain large Hausdorff dimensionality. That feature is simply not available if you go to Fourier dimension. Sets with large Fourier dimension have richer structure, and just by that property alone, they are able to contain non-trivial solutions to at least certain non-trivial translation invariant linear equations. Any questions so far?
Is the mount optimal for the the 2 by 3, is it optimal or
This one?
yes?
Good question. It is optimal for the method, but I don't think it is known whether this is so. That's a great question. So let me thank you for asking it. Let me make a note. So sharpness not known. Sharpness unclear. But there is something that is known, and let me say in what sense what is known that might give you some indication of the sharpness. So what is known is that suppose, so I'll put a star here. Suppose that the dimension of E is positive. Sorry, I got this. The Fourier dimension of E is positive. So just anything positive will do. Okay. Then there exists an integer V, and coefficients A1, A2, A V plus 1 in the integers such that E contains a non-trivial solution to some equation of the form and these ones have to be also translation invariant, so they have to obey the property that AV plus 1 equals summation AI. So this is a sharpness statement of a different type. even if the Fourier dimension falls below 2/3, but still remains positive, one can ensure a non-trivial solution of some translation invariant linear equation, perhaps in more variables.
Thank you very much.
Okay. Any other questions?
Do we know anything about how many triples ABC, for how many triples ABC there will exist today? So of course for any
Yes,
scaling of
there,
ABC we'll have,
of course,
but
that's right.
anything beyond that?
Yeah. So there are a lot of things known about it. So, for example, it is known that if you choose any finite collection of ABC, however large, one can actually create avoiding sets which would avoid the finite, those non-trivial solutions of those finite quantities. There are similar, one can take it to an extreme. One can take a countable collection of triplets ABC and still manage to find a set of Fourier dimension um, positive, which avoids those. If you are wanting to know how many ABCs does it contain, the proof is actually going to give you some idea of the Hausdorff dimension of triplets ABC for which such non-trivial solutions will be available. So maybe what I can do is I can try to show you the proof and you can see how the size of ABCs which obey this property falls out of it. Okay?
Okay, sure. Thank you.
Okay, great. So what I'm going to do is in the rest of the talk, I will try to sketch a proof of the theorem. So sketch of proof. So I'm first going to write down the proof, and it's going to have all kinds of holes. And then I'm hoping that you can point me to where all these holes are, and we will go ahead and fix them, and hopefully that'll work. Okay. So what I'm going to first talk about is something called a configuration integral. Okay. So what does this do? Let's look at the equations, the type of equations whose solutions we are trying to find. So these would be ax plus by equal to cz. And because it's translation invariant, we can write this as tx plus 1 minus ty equals z, where t is a over c, and it's a rational number between 0 and 1. Whoops. And 1 minus t is b over c, which is also a rational number between 0 and 1. Okay. So this configuration integral that I'm going to construct, I'll call this lambda t. And what it will try to do is it's going to try and pick out whether the support of the measure mu has any non-trivial solutions of this type. So let me try writing this down, okay? So I'm going to write this as mu of x, mu of y, d mu, I'm sorry, there is a third one, tx plus 1 minus ty. Okay, and I think that's it. So this is dx dy for a given t, and and there has to be a function f, and I'm going to keep this as f of xy. Okay, so this is an object which acts on a function f, and the claim is that this is 0 for all f if f has no non-trivial solution. And I'm expecting you to ask lots of questions at this stage, so I'll stop and see what your questions are. So it's this object here is called the configuration integral because what it does is it creates an analytic way of determining um, whether the support of your measure mu contains, sorry, I didn't write it the way I wanted to, if the support of mu has no non-trivial solutions. Mu is a measure. So mu is a probability measure supported on E. And I claim that if the support of mu has no non-trivial solution of this equation, then this quantity has to vanish identically for all test functions f. Any questions so far?
Mu x is measure of the singleton x, or
Could you say that again?
what is mu x? Measure of the
Right,
singleton x, or
right. Very good. So right now, mu is a probability measure on E. So, and I think you asked the right question, and I'm waiting for the. So what? So you asked what mu is, and I said that mu is a probability measure supported on this set E. And
right?
I'm hope
Mu of
yes,
x is mu of the singleton set x, is it?
no.
No.
So no. So this is really exactly the right question. So this is let me clarify. So remember that capital E is a subset of 0, 1. It is Lebesgue null. So
Right.
the Lebesgue measure of the set E is 0.
Right.
Mu is a measure whose support is a probability measure supported on E. So, and you asked exactly the right question. So, what does mu of x mean? Because it's a Lebesgue null set. And that's the question that I was asking for because typically these are measures, these are generalized functions, these are not actual functions. So, how do we actually make sense of them as functions? Well, we convolve them with an approximate identity and then they become functions. So, this is like a delta, an epsilon thickening of mu. Phi epsilon is an approximate identity, and I'll draw a picture in a moment. So these are C infinity functions, and they look like they approximate the Dirac delta. Okay. And these objects, which just by saying mu would not make sense, becomes meaningful if you replace it by their thickened counterparts mu epsilon, and you let epsilon go to 0. So this is the way to make sense of this integral, which, as you pointed out, by itself is not meaningful. Does that answer your question?
Yes, but it is not clear that the limit exists.
That's exactly the point. Right now, if I just write down a limit epsilon goes to 0, doesn't mean that it exists. So the entire point is hope if this exists, then perhaps this claim will make sense. So what's
Oh,
the guarantee why does this exist? So
Thank
why
you.
does the limit exist? So let's try to understand why we should even believe that this limit exists. And this is where this Fourier dimension property comes in. That's really the whole point of this exercise. So mu epsilon, so let's remind ourselves of the Fourier inversion formula. So recall that mu epsilon, the C infinity function, can be written using the inverse Fourier transform e to the 2 pi I tx plus 1 minus ty xi mu epsilon hat of xi dxi. Okay, so this is Fourier inversion. And what I'm going to do is I'm going to plug this formula into that this configuration integral above, and let's see what happens. Okay, so if we do this, so let's lambda t mu of 1, let's just take the constant function 1 and see how that works. So this is going to be mu epsilon x, mu epsilon y, and then use the Fourier inversion on the other part. So 2 pi I tx plus 1 minus ty times xi, mu epsilon hat xi dxi. And then we have a dx and a dy. And this gives rise to some nice simplification. You see, and there is a limit here, of course. Eventually, we'll have to check that this limit exists. That's the point. So let's see. If I do the x integration first, so there is a tx xi here and then x here. So this is mu epsilon hat of negative t xi. Similarly, if I look at the y integral, there is a y here, and that gives me mu epsilon hat 1 negative 1 minus t xi. There was this third xi integral sitting around, so everything collapses and becomes a single integral. And we are still trying to figure out if this limit exists or not. All right. Now recall, what was mu epsilon? Mu epsilon was an epsilon thickening of mu. So mu epsilon hat of xi, because the Fourier transform turns convolutions into products, this is mu hat of xi times phi hat of epsilon xi. Okay, so this, each one of these is just becomes mu hat of negative t xi times phi hat of, or phi epsilon hat of negative t xi, and this is true for everything. Now, in order to show that the limit exists, apply the dominated convergence theorem. What does the dominated convergence say? So it says that you can pull the limit inside the integral, provided, so this will work if, so this object goes inside, and once it goes inside, it's going to, the limit of this is going to be equal to 1. So everything, so dominated convergence will say that this is equal to the integral mu hat of negative t xi mu hat of negative 1 minus t psi mu hat of psi. And in order to apply dominated convergence, one has to check that this integral, this is absolutely integrable. So is this absolutely integrable? And this is exactly where the Fourier dimensionality comes in. You see, because the integrand, this product here, is less than or equal to absolute value of psi. There is a constant that depends on t, and I won't worry about it. But the decay condition says that this is to the power of negative 3 beta over 2. Why 3? Because there are three factors, each one contributing a factor of beta over 2. And you want this to be integrable. This is integrable because 3 beta over 2 is larger than 1. In other words, beta larger than 2/3. So that Fourier dimension condition of beta being larger than 2/3 is precisely what is needed to make sense of the configuration integral. Okay, so it ensures that the limit exists, and once the limit exists, it's not too difficult to see that this is an object that captures the correct pattern. Okay, any questions so far? Please do ask questions, because my goal is not to lose all of you, rather to answer the questions that you have. So if it's completely normal to have lots of questions. Please ask. Okay. If not, then in the remaining 5 minutes or so, I am going to try and show why having Fourier dimension larger than 2/3 forces the set to contain a linear pattern of some rational three variable equation. Okay, so we are going to prove this by contradiction. So let's assume if possible that E contains no non-trivial solutions of any equation of the form tx plus 1 minus ty equals z. So what we are going to do is we are going to reach some kind of a contradiction in the following way. So let's start with the measure mu epsilon x dx. So remember, this mu epsilon is mu convolved with phi epsilon, so it's a probability density. It has measure 1. Okay, so this is where we start. And I'm going to actually take 3 copies of 1 and cube it and write it as 3 integrals. Okay. Now, this is a symmetric and then integral, which is symmetric in x, y, and z. What that means is that if you permute x, y, and z, the integral remains unchanged. So I'm going to write it as 3 factorial times the same integral but with a very specific ordering. So I will write this as x less than z less than y. Okay. Okay, so far so good. Now, let's draw a picture because I'm on to make a change of variable very soon. So here is x, y is on the other side, z varies somewhere in between. So I want to make a change of variable, and the change of variable is to say that replace z by t, and z is going to be tx plus 1 minus ty. So the old variable z is replaced by the new variable t. Okay. All right. So let's take a look at what happens here. So make a change of variable. So this becomes mu epsilon tx plus 1 minus ty. We pick up a Jacobian. So dz becomes um, absolute value of x minus y, or which is actually y minus x. Okay. And t goes from 0 to 1. So um, all told, this becomes x and y, x is less than y, that still stays. T goes from 0 to 1. And what we are left with is mu epsilon x, mu epsilon y, mu epsilon tx plus ty, tx plus 1 minus ty, absolute value of x minus y, dx dy. In fact, what I'm going to do is I'm going to reorder this integration. I'll put the t integral outside. So let's put t integral outside. And instead of saying make it less than or equal to the double integral of x and y inside. Okay. Now I claim that this integral inside is something that you ought to recognize because this is exactly how we defined our lambda, our configuration integral. So this object here is really our configuration integral. So let's take the limit. So if you take this as, put in a limit here as epsilon goes to 0 and the limit as epsilon goes to 0 and bring it all through and dominated convergence will also again allow you to bring the limit inside. So what are you left with? You are left with the integral from 0 to 1 lambda t mu of f dt. What is f? F of x y is this. This is f of x comma y. Okay, so let me get to the punchline. If we remember, we assumed that there are no non-trivial solutions of these types of equations, and t here was a rational. T was any rational in 0, 1. This object here is a continuous function of t. And it vanishes at all the rational points of t. And you know that continuous functions that vanish on all rationals must vanish identically, which means lambda t mu is identically equal to 0 for all t. What does that mean? That means that this entire right-hand side is 0. And this obviously cannot be true because we started from 1 on the left and we showed that 1 is less than or equal to 0. That's a contradiction. And that's what we are aiming for. So what this shows is that and everywhere along the way, we have to keep using dominated convergence theorem to switch limits and integrals. And every time we do this, and even in order to make sense of the configuration integral, we are implicitly using the Fourier dimensionality of things. Incidentally, so you asked me, can one say how many ABCs there might be? Well, this will tell you that there has to be a set ABC. This ABCs actually relate to the T's. So there has to be a set of positive measure worth of T's for which there has to exist a solution. So in fact, you can turn this argument into a quantitative statement. Okay, so this is the sketch of proof I wanted to tell you today. I will stop now and let you ask questions.
All right, thanks a lot for the talk. I don't think I have much of the background needed to fully appreciate this, but I wanted to understand this configuration integral a little more.
Yes.
Uh, could you go back up to the definition?
Here, this one, right?
Yeah.
Yeah.
So, is there some intuition as to why this kind of thing should capture these kind of discrete properties of
Uh, why this should capture existence of solutions?
yeah, or just some this kind of discrete property in general? Why this kind of object does that?
Oh, okay. Okay, let me see if I can. Maybe I didn't fully understand what you meant by discrete properties, but let me at least say something and see if that addresses your question. Okay, so suppose for the moment you assume that there is you have a set, okay, a good set. So let's take a set capital E, and let's ask, um, and is a set of positive measures, so there are no funny measures and things. It's actually an honest to goodness positive Lebesgue measure set. So I want to check if this set E contains, let's say, any arithmetic progressions. So what would I do? I would look at this the indicator E of X, the indicator E of Y, and the indicator of X plus Y over 2. Okay. So suppose that I integrated this object in X and Y and found that this object is positive. Would you agree that the positivity of this integral would then say that AE must contain 3 APs?
Yeah,
Why? Because then that means there exists X and Y not equal to each other, for which if the integral is positive, the integrand must be positive somewhere, and that would signal the existence of a 3AP.
yeah,
Agreed? This is exactly borrowed. Whoops, where did I go? This statement here, where is my configuration integral? Somewhere up here. Yeah, right here. Do you see that this is exactly borrowed from there? This is like indicator E of X. This is indicator E of Y. And this is indicator E of Tx plus 1 minus Ty. As long if E was a positive Lebesgue measure set, this would make perfect sense, but our sets E are sparse. They are all Lebesgue null. So instead of indicator functions, we have to fall back on measures. That's the only difference.
I see. That makes sense.
Okay.
Yeah, thanks for that.
Okay.
Malabika.
Yeah.
So actually, I was just wondering, the way that you have done it. So when I look at this configuration integral, the whole thing is somehow making me feel that the phi epsilon is playing much bigger role than the mu, isn't it? I'm not sure what I'm asking, but see, mu epsilon is essentially mu convolved with phi epsilon, right?
Yeah, yeah, exactly. But you see, as here's the thing, the limit gets rid of all the dependence on phi epsilon. Why is that? That's because when you look at mu epsilon, which is mu convolved with phi epsilon, this converges to mu weakly in the weak star topology as epsilon goes to 0. So really, the phi epsilon is introduced to create actual honest to goodness functions out of a measure so that this integral makes sense. But by taking the limit as epsilon goes to 0, we kind of remove the dependence on phi epsilon entirely. If we had if we had not had the limit, if we had left it just as a mu epsilon, this configuration integral would not have been strong enough because it would have been a C infinity function. Its support would contain intervals, and of course, intervals contain all possible configurations. But by taking the limit to 0 and then showing that this configuration integral is still positive, that's what helps us out in the long run.
Okay, thank you.
You are absolutely right. If we had fixed an epsilon and done the entire analysis with that one epsilon, it would have shown nothing.
Thanks a lot.
Okay.
Yeah, there's a question from student here.
Okay.
Hello, ma'am. I had a
Yes.
generic doubt.
Yes.
So, we showed that for these kind of patterns, large sets in some sense can never have, cannot be free of those patterns.
Correct.
So, is there any relation between class of patterns and some type of measuring how big a set is, such that, for these kind of patterns, large
Yes.
sets in some other sense can never be free of them? Is there some correspondence between?
Yes, that's a very good question. That's an excellent question. I mean, that is also a area of inquiry. Let me repeat the question so that just to make sure that I understood your point. So what you said is that what we showed yesterday that if we look at linear patterns, then there can exist sets of large Hausdorff dimension that can avoid all such patterns. In contrast, today we showed that if we look at sets of Fourier dimension, then they must contain some non-trivial linear pattern. Your question is coming from the opposite end. Are there patterns which certain large sets are bound to carry? Is that the question?
Yes, ma'am.
Okay, great. So let's see. The answer is yes, very much so, and I'll give you an example. So see. So there is a distinction. Today I talked only about linear patterns, and these are um, for example, today it was of the form ax plus by equal to cz. But we could also consider, for example, nonlinear patterns. Okay, so what would a nonlinear pattern be? For example, it could be like points on a parabola, for example. So let's say z minus x is equal to y minus x squared. Okay. Now, it's expected, and there's some evidence supporting this, that if a set E is contained inside 0, 1, and it has Hausdorff dimension larger than a half, it must contain distinct XYZ obeying star, and star is this quadratic pattern. So in the way I have stated this here, it's an open problem, but there are many versions known in higher dimensions, not on R. Um, so the short answer to your question is that linearity versus nonlinearity poses a big difference in this field. Nonlinear patterns are somehow embedded in sets of large Hausdorff dimension. That's the meta principle, but linear patterns are not.
Thank you very much, ma'am.
You're welcome.
Hello, ma'am. I just
Yes.
have a sort of follow-up question to the previous one asked.
Yeah.
So has there been any work done in sort of proving theorems of the form, something like Fermat's last theorem, things like that, using avoidance sets of this nature, something like that?
Well, yes, of course. I mean, I don't know about Fermat's last theorem. I don't know if there are any applications there, but many of these kinds of techniques that I talked about, they have come from results like in number theory, like Roth's theorem, um, Zemerides theorem, and most recently, I think the results of Green Tau about progressions in the primes. So if you, for example, look at Tau's Elescorial lecture notes online, you are going to see that it talks about very similar things in the integers. There are configuration integrals that have to be shown to be positive, configuration integrals that capture progressions, and the positivity of that configuration integrals, and together with some randomness properties, and the randomness should be considered analogous to this idea of Fourier dimension. Those things, these ideas keep repeating in these kind of pattern formation problems. Remember, configuration integrals are used to prove existence of patterns. Avoidance of patterns typically uses constructions of avoiding sets. So that's a different beast entirely.
Okay, thank you. Thank you so much. I'll check these
Yeah.
out later. Also, I have a completely unrelated question.
Mhm.
Do you mind if I ask it right now or after somebody else's question?
If somebody else has a question, let's see if we get all the related questions out of the way, and then we'll circle back to you.
Sure, ma'am. Thank you so much.
If you have the time, I also wanted to ask if there was intuition for why the Fourier dimension is a notion of dimension. I didn't fully get that either.
Okay. So, um, let's see now. All right. When you said you wanted to understand why the Fourier dimension is a notion of dimension, okay, this one, right? Um,
Yes, yeah.
all right. So, let's ask you a counter question. What do you expect a dimension to be?
Um, it should be some measure of size along with something else. And
Yes.
I'm not sure how to put my finger on that something else.
Exactly. No, no, no. That's exactly the right answer. I mean, it has for small sets, the dimension has to be small. For large sets, the dimension has to be large. But then there is something else in between which is difficult to put a finger on. And in fact, there are a lot of different things that you would like to put your finger on. You see, Hausdorff dimension tries to capture something related to coverings of sets. Okay? Fourier dimension tries to capture the spread of a set, but in a different way. So let me extra, and it's all trying to make sense of something that is
Right,
intangible.
right.
Now, let me try to say what the intuition is. So the intuition is, and this intuition is partly right and partly wrong. The more spread out a set is, the more likely it is to support measures mu with Fourier decay. And I'll explain why that is in a moment with Fourier decay. Okay. Why is that? So remember, this is the definition of mu hat. Okay. And whoops, what did I do? My mu hat just vanished. Okay. So mu hat of xi has an oscillatory factor e to the power minus 2 pi I xi d mu x. Now you see, these oscillatory factors, these are really just combinations of sines and cosines, right? So you should think of this integral as really a superposition of sine cosine waves. So the more points there are in x, the more sine and cosine curves there will be, and there will be a greater chance that they cancel each other out, leading to Fourier decay. Okay, so that's the intuition. So the Fourier decay, this condition really says that there are so many different points inside of the support of mu, so many different points x, that they can, when you look at the superposition of those using this mu, there is actually a lot of cancellation in mu hat of xi. And that is a way of determining size. Of course, as I have just proved to you, this is not entirely consistent with the other existing notions of size. There is something very distinct about it. For example, this Cantor middle third set, its Hausdorff dimension is quite large, but its Fourier dimension is zero. In spite of it being an uncountable set, its points are such that it cannot support any measure with Fourier decay. So this
Right.
intangible thing that you are trying to put your finger on, the way it is being quantified is that if there are many points inside the support of mu, you can think of it as a superposition. If it was a discrete measure, it would be the product of some weights, and then some e to the power of negative 2 pi I xi psi. It would be like this. And you would want to make sure that this, for xi's, this is really small. That is only possible if you have many, many xi's. Because if you
Correct.
have only one or two, there is no reason to believe that this will be small. It needs many x's in order to get decay of mu hat of psi. And that's the notion of size.
That makes sense. Thank you very much.
Thanks.
Malabika,
Yes.
I mean, I don't know whether it makes sense at all or not. See, the condition that you have got when you are defining the Fourier dimension, and that is supremum over xi in R, when you're looking at
Yes.
modulus of mu hat at xi times mod phi
Yes.
to the beta by 2 is going to be finite. So in some
Yes.
sense, you're saying that this mu hat, and if at all I look at it in terms of functions, so mu has got some kind of a smoothness. That is the kind of thing that is just giving me. And so I don't
Yes.
know really, I mean, what does it mean by, I'm looking at a measure and
Yes.
in the Fourier transform of it, and I'm asking this condition to hold,
Yes.
right? So what
Yes.
I mean, so why is that? So that is what I mean. Why is that something like that is talking about giving me some understanding about E? I I really cannot understand this. So
You're asking why this condition here
yeah,
gives
so
me
this condition
any
here is telling me so E supports a probability measure which has got this kind of a property.
yes. But are you asking why it
Yes,
says anything about E?
yes, yes.
Yeah, so I think this is something that I was trying to explain in these examples. So
Yeah.
if you
So
take E to be our singleton or a finite collection of points, then
right,
what kind of measures would be supported on such an E? For if E is the singleton 0 or singleton any point, the only probability measure it can support is the Dirac delta,
right,
and that has no decay,
right, right. Absolutely.
right? So, similarly, on the other end of the spectrum, if you take an entire interval, then you have an immensely rich collection of probability measures on it. For example, you can talk about smooth functions of compact support. You can talk about infinitely differentiable functions. You can talk about the indicator functions. There are so many probability densities to choose from that are supported on 0, 1, and they have great decay properties. So one way to think about it is the smaller a set is, the more restricted you are in trying to find measures that are supported on it. The more points a set E has, you have a richer collection of possible mu's.
Right. I understand. Yeah. Okay. Yeah. Thank you very much.
Welcome.
I missed out somehow. Yeah.
Malabika, so I in the statement that you have proved here only assumed that the set has large Fourier dimension, right? That it has
Yes.
Fourier dimension bigger than 2 by 3. So I'm a
Yes.
bit confused here because I thought Shmerkin had given this example of sets with large Fourier dimension that does not contain
Yes.
three-term arithmetic
Yes.
progressions, right?
Exactly. That's a great question, and in fact, hopefully we don't contradict each other, because then we are in trouble. So,
Yeah,
so it's important to understand what it is that Schmerkin proves and why this result complements it but doesn't run contrary to it. So let me state Schmerkin's result, and then we can stare at this together. So as Ashwin was saying, this is the result of Schmerkin, which shows that there exists a set E, subset of 0, 1, Fourier dimension of E is 1, and E has no three-term APs. Okay, so basically that means no solution to x plus y equals to z. So I want you to look at the main theorem, compare it with Schmerkin's result, and explain to me why there is no catastrophe. Why these two statements can stand side by side and give a clearer picture of what is happening. Did my theorem say, so obviously if the Fourier dimension is 1, it's greater than 2/3. So my theorem should apply. Why does this not contradict Schmerkin's theorem?
This is for some ABC, it's not for all.
Exactly. It's for some. So all this says is that if you look at Schmerkin's result, it will not contain any non-trivial solution to this, but it cannot avoid all such solutions. For example, it may contain an solution to an equation like 4x plus y equals 5z, or 10x plus 15y, or 16. Uh, I can't write something. Things just keep slipping away from me. So, or some equation of the form 13x plus 5y equals 18z. So in Schmerkin's case, these kinds of equation were not of interest. It was only what was interesting was three-term APs, and this particular set that he constructed avoided all such solutions. But in the process of doing so, our result says that it has to let in solutions of other types. It can avoid some, it can avoid solutions of one equation, maybe finitely many equation, perhaps even countably many equations, but it simply cannot avoid all possible solutions if the Fourier dimension is of all possible solutions to all possible equations if the Fourier dimension exceeds 2/3. Does that make sense, Ashwin?
Oh, yes, thank you. Thank you. I misread the statement. Thanks.
It's like you can you can escape some, but not all. That seems to be the principle.
Hello, ma'am.
Yes.
If the rest of the questions are over, I don't want to rush anything, but if the
Yeah,
rest
please
of the
go
questions
ahead.
are over,
Yes.
okay. My question was just, would you recommend any good resources to find open questions and just general things that researchers are working on? Any resource that's sort of accessible to undergraduate students, since it's just cool
Okay.
to punch above
Yes.
your weight class every once in a
Yes.
while and
Of course.
just be exposed to these problems.
Sure. Okay. So maybe I'll start with something that's probably interesting news. Um, there has been a lot of talk recently. There's been a lot of excitement because one of the major open problems in harmonic analysis, called the Kakeya conjecture, which is also at heart a pattern problem, there has been a proof of it that has been posted on Archive due to Joshua Zal and Hong Wang. So that's a very exciting development in the field. I do not want to give you the impression that this is this is undergraduate material. It is not, but if you look at, it's a good time perhaps to try to get a sense of that field. If you want a beginner's guide to the Kakea problem and its many repercussions in harmonic analysis and geometric measure theory, start with Stein and Shakarchi's undergraduate books in analysis. They're extremely well written. From that, I would say if you have a good grasp of those, Matila's book on what is it called? Hausdorff dimension and Fourier analysis and Hausdorff dimension.
That's right.
That book, yeah, that book is also has a bit more advanced rendition. It's a graduate text. So if you have made some headway with Stein and Shakarchi's undergraduate analysis books, then take a look at Matila's Fourier analysis and Hausdorff dimension, which talks about the next level in Kakea problems. And then from there, perhaps it's a better idea to look at more, even more advanced research papers. And there can be there are many things there. For example, people like Tao, Burgan, Laba, Netskats, Hongwang, Zal collaborators, or Ponen. They have many papers. But I think that's maybe going a little too far ahead. Start with Stein and Shakarchi, Big Stein, and Matila. So that's to do with the Kakea problem. There are a host of other pattern problems which I think are very easily accessible to undergrads and actually has very nice geometric intuition behind them that makes them very appealing to visualize. And those are patterns in finite fields. So one result that I really like very much, um, it talks about large sets in finite fields which contain lots of three-term APs, but no four-term APs. So these are such interesting tweaks. And because it's in a finite field, everything is discrete. You don't have to get into any kind of complicated measure theory business. Most of it is just simple counting arguments. Um, you might want to pick up a book by Alex Yosevich as it's very undergraduate friendly. It's called A View from the Top. It gives a beginner's introduction to many interesting areas of analysis and geometric measure theory and incidence geometry. For example, the Erdős distance problem, the distinct distance problem, the unit distance problem, their relations with number theory. So that book is called A View from the Top.
Okay, thank you so much for the detailed answer. Just to double check, was the open problem that was recently solved also the one which Dr. Ashwin mentioned in, I believe it was lecture 1? Was it the same problem?
Ashwin, I
In the
have no
main
idea. You should take this one.
Yeah, I think I have mentioned Kakea conjecture, but
Yes.
yeah, I don't think I've detailed the problem.
Yes. Yes. Okay, great. So
okay,
it
okay,
sounds like it's the same one.
that's nice to hear. Again, thank you so
Yeah.
much for the detailed
Yeah,
answer.
there is another important question. There are so many open problems in the field. Another one is called the Falconer distance problem that again appears in Matila's book. There are results, there are conjectures due to Furstenberg related to these cousins of Kakea sets called Furstenberg sets. Once you start looking at some of these textbooks, you will see that there are just more questions than answers. It's a very vibrant field.
That's very cool to hear. Thank you.
Thank you.
So are there any more questions? If not, let's thank the speaker. Thanks a lot. And Malabika, it is really an honor that you
Not
accepted
at
and
all.
you gave the talks.
Thanks everyone. Thanks for being such a great audience. And I hope I will get to see some of you in 3D before too long. Bye now.
Thanks a lot for the talks.
Thank you. I'm going to end the meeting now. What is this? Just